4, 3, 2, 1, go. Okay, welcome back. We were working on 1.1 and this is part 2 of the video. And so we'll get going on it. Okay, so now we have the definition of absolute value. And oh my gosh, did I not have a pencil here? Because I have this one. That the absolute value of 9, you know, is 9. Absolute value is a distance from 0. So it's asking you on the number line, how far is it from 0 to 9? Well, it's 9 away. And how far is it from 0 to 0? Well, it's 0 away. And how far from 0 is it to negative 8? And if you're kind of thinking, you know, here's negative 8 and here's 0, and how far is that? Well, that's positive 8. Distance is positive. And so this is what we saw in our algebra class, right? And we just said make it positive. And here's really the formal definition. It's actually piecewise defined function is what it is. And it says that the absolute value of x is equal to x if x is greater than 0. And you can kind of see, or equal to 0, you can kind of see how that worked out. Because the absolute value of 9, well, 9 is greater than 0, so it's just the same, 9. And 0, same, meets that condition, right? So 0, it would be equal to 0. But for negative 8, the absolute value of negative 8 is smaller than 0. So it would be the opposite of negative 8, and the opposite of negative 8, right? Negative right there, opposite of the negative, opposite there is positive 8. Okay, so they're asking us here to write this with absolute value bars, x plus 2. And so we're going to have x plus 2, and that's going to be piecewise defined. And so I say how I fill this in is that whatever I have in here, I let it be. Whatever it is goes right here, x plus 2. And so I kind of have these 4 spots that I'm going to be filling in. And here is the opposite of that. So opposite of x plus 2. And when would this be? So this would be 4. And that would be when, and I'm going to write it up here, x plus 2 is greater than, right? Whatever you had in there is greater than or equal to 0. And this is 4. Following this, whatever you had in there, whatever you had is smaller than 0. So what I have in here is x plus 2 is less than 0. And then I'm just going to clean this up. So the absolute value of x plus 2 is equal to x plus 2 and minus x minus 2. And this is 4. And then I want to solve this. So I'm going to take away 2 from both sides of this. So this is going to be x is greater than or equal to negative 2. And 4, x is less than, right? I'm going to subtract 2 from both sides here. So x is less than negative 2. And so this is what they're asking me to write. This is the answer that they're asking. It no longer has absolute value bars in it. Okay, so we did a lovely job on that. And the next thing that they're going to ask us to do here is they're going to ask us to sketch a graph of that. And oh, I didn't get it down. Sorry, pull it down. And so when you go to sketch a graph of this, 2 ways that you can do it. You can use what you just did over here, and you can graph this. Y equals x plus 2 and y equals negative x minus 2. And you can pick points on either side of that like we did up here. And I went ahead and picked some points. This is a line and that's a line, so it's going to be 2 lines. And that would be a way that you could graph it, is to first write it without absolute value. Another way that you could graph it is to use your shifts in your translations and all of that kind of thing, and that's great too. I probably would say to myself, this is just going to be a V, right? I mean, it's something we recognize, and the vertex of that V, is going to happen at -2, where the inside here of that absolute value is equal to 0. And so the absolute value of 0 is 0. And then I would probably, since I know it's just 2 lines, I would probably, and there I have the vertex, I'd probably just pick one on either side of the vertex. So maybe I'll pick -1. They'll be on the high side of the vertex. So it'll be the absolute value of 1, which is 1. Notice that was positive. And then I'll pick something on the low side. -3 is smaller than -2. -3 plus 2, that's -1, and the absolute value of -1 is 1. And so you notice I kind of picked something symmetric there on either side so that I would have 0, right? Absolute value of 0 is 0, and then the absolute value of any negative is a positive, and the absolute value of any positive is a positive. So I kind of got myself centered there at where the change would be at the positive and the negative inside. So let's see, -2, 0, -1, 1, -3, 1, and I had a ruler here. My tools are all, I've gotten crazy, and I'll just draw it out here straight, as straight as I can. I do enjoy getting a ruler, but my ruler is, I don't know where my ruler is. So so we did a lovely job on that. One thing that I've seen people do, and I just want you to see that, hey, that would work out really great, is I've seen people graph y equals x plus 2. And you could probably pick points in your head here. If I pick 0, I'm at 2. If I pick 1, then I'm at 3. If I pick -1, well, then I would be at 1. If I pick -2, well, I would be at 0. And that line goes here, right? And then they say, well, what would happen if I put absolute value bars around that? That means that any output, y value, any output that's positive would stay positive. So these are positive. They're y values that are positive, right? Ordered pairs with y values, y coordinates that are positive, so they would stay positive. But any that were negative, and these have y values that are negative, would now become positive. And you notice, and then this would be gone, right? And now you notice that, hey, that's what we got over there. So that's a way of graphing it as well. And so the reason I mention that is because that's actually kind of what I would like to do here, is that I've got this double absolute value, and I could start by writing it without absolute value bars, but that turns out to be really hard to do that. I mean, it's possible, and if you want a challenge, I actually challenge you to do that on the next page. But if you're just wanting to sketch it, you could start off by sketching y equals the absolute value of x minus 1. And then I could say to myself, well, let me think. I know what y equals the absolute value of x looks like. It looks like this. This pencil's really dull, and that's driving me crazy, but I'm going to live with it. And so if I take away 1, what does that do to the graph? And so it just takes the whole graph, it takes all of the outputs, right? Y is the outputs, it takes all of the outputs and it lowers them down 1, right? And so this would then look like this. So lower down 1, this would be then at -1 because this was at 0. And is what that would look like, right? Okay, so we started off by saying, hey, I want to sketch y equals absolute value of x and then minus 1. And then we said, oh, let me sketch y equals absolute value of x, which we could do easily. And then now I'm saying, well, what I'd like to do is I want absolute value around the outside of that. And so what does that do? It takes all of the outputs that are positive and leaves them there. And so these are positive. And it takes all of the outputs that are negative and makes them positive. So they're going to come up here. So where is this crossing right here? Can you think of where that would be crossing? Yeah, so since the y value there has to be at 0, it has to be that that's crossing right there at, do you guys agree, -1, right? Because that would be the absolute value of -1 is 1, and 1 minus 1 is 0. So this is at -1, and this is crossing at 1. My graph's getting a little silly. So right here, I should have changed that number, and then it would be a little bit bigger. So here I am at -1, and here I am at 1. And we know here, and this is going right here. I'm drawing it without a ruler. Okay, so that's going right there. And then we had this over here going. And then we had this part that was down here at -1, and this whole thing was going to be made positive. So the whole thing is going to go above. So this is going to, it was at -1, so it's going to go up to 1. And then I'll just sketch the rest of it in. So there you have it, a way of graphing it. And we did a lovely job at that. And so they're asking us on the next page, on page problem, I said, for those who want a challenge, I'll bring it down so that you can see it. For those needing a challenge, write this without absolute value bars. Now, if you write it without absolute value bars from the graph, then it's not very challenging. There's 4 pieces, and you can easily do that. But if you try to write it without absolute value bars, not thinking about the graph, it actually is quite challenging then. And I'm not saying they have to always do things the hardest way, but if you were wanting to, so do it any way you want. That would be wonderful. And so anyway, so I'm going to leave that to you for the challenge. Okay, and then just making sure, and so I just want to make sure that everyone kind of sees that whatever you have in here is going in these 4 spots, and then you're fixing it up. So since I have in here 3x minus 2, right here would be 3x minus 2. Right here would be 3x minus 2. Here would be the opposite of 3x minus 2. And right here would be 3x minus 2. See how here it's the same, the same, the same, and that one spot, it's the opposite of it to get it going, right? And then you would need to, so this is 3x minus 2, there's no problem here. And over here, you would need to solve that. 3x minus 2 is greater than 0, so you'd add 2, right? You get 3x is greater than or equal to 2, and then dividing by 3, you wouldn't have to flip the sign there, so you would get is greater than or equal to 2/3, right? So this is x is greater than or equal to 2/3. And here you have negative 3x plus 2. And if you solve this and you do the work on it, notice it's the same except for that symbol right there. These are exactly the same except for greater than or equal to and less than. And so this is, I'm going to be lazy, this is just going to be x is less than 2/3, whatever you had there. It'd be the same. Okay. And then they're asking me, hey, graph this. And I'm just going to tell you that, hey, you could use various methods of graphing it. You could use all your transformations and all that. You could graph this piecewise defined function right there. You could graph this line and then apply the absolute value, or you could pick a few good points. And it really is your choice on how you would do that. And they're all I think, good ways of going. A lot of people tell you that they don't like to pick a few good points. And I have to admit that I'm a point picker. I do like to pick good points and put them on there. When you're picking good points, it requires that you know some things about what it's going to look like. And so you kind of know some things about the transformations and those kind of things whenever you're picking points. So for me, I would say a good point would be to pick is where the inside right here is 0. And we know where the inside of this is 0 is at 2/3. So I would probably pick 2/3. And then this would be y equals, it would be the absolute value of 0, which is 0. And then I would want to pick, so now I have here's 1, and here's 2/3, just right there. So there I am, there's 1, right? And then I would want to pick something like maybe 1, because I want to pick something on this side. I know that that's just a line on either side. So when I pick 1, then I'm getting, y equals the absolute value of 3 times 1 is 3 minus 2, right, is the absolute value of 1, which is coincidentally 1. So 1, 1. And then I could maybe pick 0. When I pick 0 on the other side, I get the absolute value of 3 times 0 minus 2. So that's the absolute value of negative 2, which is 2. And so I'm up here at 2. And I'm at 0, 1, 2. Okay. And there I've made a sketch of it. And so you can use whatever method that you want to make a sketch of it. And I'm good with all of that. I don't know why I didn't have a grid here for me to put it on, but I didn't. And so I sketched it. Great. Okay. The other thing that we have, and I like it better on my computer screen, because when I have this on my computer screen, and I know that you're probably thinking you probably could do this with a pen on the computer screen instead of the way that you're capturing it, and I know that I probably could. I don't own a tablet or something, a writing thing like that. I have considered getting one. I'm not terribly tech savvy, but I also don't like writing on them. And so I like writing on paper. And so anyway, call me old. So anyway, here they're talking about the secant line. And a secant line is a straight line that is joining 2 points on a function. And so here are the 2 points, P and Q, and the line that joins them is called the secant line. And then the difference quotient, you probably heard that term thrown around in your math analysis class, whether you took the math analysis class at Bakersfield College. I think we call it pre-calculus, and a lot of high schools call it math analysis. Some high schools call it pre-calculus, whatever, same class. And so whenever you took that class, you probably heard the difference quotient, and the difference quotient is going to be a really useful thing in calculus. And so anyway, so the difference quotient is just the slope of the secant line. And I just wanted to show you that these are going to be two different symbols to represent the difference quotient, but they're exactly the same. And so if I call P x comma f at x, and so this is right here this is the x-axis, right? And this is a generic x. So I don't know, that could be over there 4, or that could be over there 5, whatever it is. And then this distance right here at Q is x plus h. So this is just h further over there. So if this was 4, and this h was 1, then that would be 4 plus 1 is 5. So this would be at the place 4, this would be at the place 5, but x means generic, it could be any value over there. And so now when I start looking at the ordered pairs that I have, is if this is at f, x, and this is the function f, so this is the function y equals f at x, then the y value would then be, when you plugged in x, would be f of x. And when you plugged in x plus h in there, it would be y equals x plus h, right? F of x plus h. So anyway, so this is my, if I use my slope, this is my x1, y1, and this is my x2, y2. And I just use the slope here, which is y2, which is f at x plus h, minus y1, which is f of x, all divided by x2, which is x plus h, minus, right, minus, and then x1, which is x. And then long story short, x minus x is 0, so we just get h in the bottom, so the slope is f at x plus h minus f at x over h. And this slope is called the difference quotient, and it represents the slope of this secant line. And another way that the secant line could be looked at, instead you could call this point here A, so that this ordered pair would be x would be A, and this is again the function y equals f at x, right? So when I plug in A in there, A goes in there, so y would be f at A. And if I called this here at Q, if I called this x, this is representing the x-axis, is what it's representing right there, right? But this, I'm going to call this point x there. Then this would be, plugging in f, would be f at x, right? So then I would have my x1, y1, x2, y2, and we would have our slope is y2, which is f at x, minus f at a, divided by x minus a, right? And that's another difference quotient, another way of looking at the difference quotient. And it's just notation different. And there's times when this is a little easier on our math, and there's times when that's a little easier on our math. So they actually in the problems ask you to look at both of them. And so that's the first story there. So here they're asking us to evaluate the difference quotient for the given function and simplify your answer. And this is the difference quotient that they have given. And so if we kind of look to see, well, which one does that sort of look like? It looks like this one, doesn't it? But instead of having A, what did they use instead of A? Yeah, they used 1. So we'll give a try to evaluating that difference quotient like they're asking here in problem 30. So when I have, this is f at x minus f at 1 over x minus 1. So f at x says come here and in your function put in x. So, well, that's already there, right? So x plus 3 over x plus 1. So this, I'm going to put a box around it, is just this. Minus, and now I'm going to get this. Well, this says go here to the function and put in 1. So I'm going to put in 1 in all those spots. So this is going to look like 1 plus 3 over 1 plus 1. So I'm going to put that in a box as well, that box, divided by, kind of got low on my equals on my divided by. I have this situation where I'm looking at my paper and I'm also looking to make sure that my paper hasn't got off the screen, and so that sometimes gets me a little bit crazy on how I'm writing, but I'll get better at it. I did last semester, and so I'm kind of starting again. This doesn't say go to the function called f. This just says x. So down here we just have x minus 1. And it's asked us to simplify our answer. So we have some things that are not simplified, like 1 plus 3 is 4, and 1 plus 1 is 2. So those are things, for example, that are not simplified. So this right here is 4 over 2, right? And hey, 4 over 2 is 2. So at one time, I'll just simplify that to be 2. So this is x plus 3 divided by x plus 1 minus 2. All divided by x minus 1. And that's not simplified because that's called a complex fraction. And what a complex fraction is when you have a fraction in the numerator of your fraction or in the denominator of your fraction or in both. And this time I have a fraction in my numerator. So looking at this as my main fraction bar, right? And this is the numerator, and this is the denominator. Well, in the numerator, I have a fraction. There it is, right there. And that's called a complex fraction. And it's not simplified to have a fraction within a fraction like that. So we have methods of simplifying it. In our algebra book, in the beginning algebra class I teach, they have two methods, and they call the methods Method 1 and Method 2, which is not very, doesn't explain to you what the method is. And you can use either method, it doesn't matter to me. One of the methods is basically the order of operations. And what it would mean to simplify this using the order of operations. And since I have time on the video to show you both, I am going to show you both. And this is the only method that I knew going through getting a master's degree. It wasn't until I taught beginning algebra that I learned the method. And I was like, oh, the other method. And I was like, oh man, that other method is really, really nice. And so anyway, so I call this method the order of operations. My textbook actually calls this method 1 in my algebra textbook. So what you do is you work on the numerator to get it simplified under the order of operations. The numerator of a fraction, order of operations, is gems, right? Grouping symbols, exponents, multiplication and his best friend division, and subtraction and his best friend addition. You can also use please excuse my dear Aunt Sally if you want. PEMDAS, people say, and I don't care which one that you use. I use please excuse my dear Aunt Sally all through my math career. Please excuse my dear Aunt Sally, right? But the reason that I have gone to gems, or that I stopped using please excuse my dear Aunt Sally, maybe I still use please excuse my dear Aunt Sally to myself, is that a lot of people think that multiplication comes before division, and it doesn't. It's on the same line, as multiplication and division are on the same line. So actually you can have a problem that has multiplication in it and division in it, and the division would come first. And the same with add and subtract. You can have a problem that actually has add and subtract in it, and it's possible for the subtract to come first. And so it's left to right is what it is. It's not. And so I always got problems wrong, whether the division came first and the subtract came first, because I thought multiplication somehow came before. And so that's the reason that I've kind of gone to this, and I say multiplication and his best friend division. So anyway, we're in the grouping symbol. And the numerator of a fraction is a grouping symbol. And parentheses, well, some people would tell you when they use please excuse my dear Aunt Sally that there are parentheses around the numerator of a fraction to make it into a grouping symbol. So to put the parentheses around it to say that, hey, they're here. So I don't care if you put the parentheses there or not, but if you're wondering why, hey, there's no P there. Well, the P was implied, but I kind of like grouping symbol better, and I like to tell myself that the numerator of a fraction is a grouping symbol. So the numerator of that fraction is not simplified, so that's where I would need to be working. The denominator of the fraction actually is okie dokie. And so what I'm going to do is I'm going to get a common denominator. So I'm going to write this as 2 over 1, because making my whole number into a fraction. And then the common denominator, because this is 1, is just whatever this is. So I'm going to multiply the top by x plus 1, and I'm going to multiply the bottom by x plus 1. And when I do that, I'm multiplying 2 by 1. X plus 1 over x plus 1 is 1. So I'm multiplying it by 1. And so this is going to end up being then x plus 3 over x plus 1 minus 2x plus 2 over x plus 1, and the denominator is just x minus 1, and I haven't changed anything about the denominator. And now I want to distribute that negative, right? There's parentheses here, implied parentheses here, and that negative is going to go with the negative 2x, and also with the 2. I'm going to have to distribute that negative. So this is going to become x plus 3 minus 2x minus 2 all over x plus 1 all over, right? Because that's the common denominator, all over the common denominator, all over x minus 1. So when the dust clears here, I have x take away 2x is negative x. Still trying to draw that a little bit deeper. And so this is minus x. And I have 3 take away 2, which is positive 1, divided by x plus 1, all divided by x minus 1. Okay, so now I've got the grouping symbol, the numerator of the fraction. I've made it look nicer. The denominator didn't need anything to be done. There's no exponents. There's no multiplication, but there is division. So now I have this divided by that. And so I can even write it so that you can see it. It's x plus 1 over x minus x plus 1 over x plus 1. So that's my numerator divided by, right, x minus 1. Well, how you do a division when you have fractions is that you, I'm going to write this as a fraction as well, just like I did when I had a subtraction between a whole number and a fraction. I wrote this as a fraction. And how you do division is you rewrite the division as a multiplication. So this is minus x plus 1 over x plus 1 times, and then you write it in a division, because remember, divide is defined, that's my division symbol, defined to be multiply, right? Multiply by the reciprocal. I wonder if I'll be able to spell reciprocal today. I'm not a very good speller, and I probably shouldn't just admit that out. I should do better on my spelling, but it's because I don't practice my spelling. So sometimes people tell me they're not very good at math, and it's because you don't practice your math. If you start practicing it, you'll get very good at it. And if I started practicing at spelling, I would get back to being good at spelling again. I was good at spelling at one time, and so but you know, with all the technology, my phone doesn't even trust me to write something. Now, if this, you know, I've made it into a multiplication. I can physically multiply these together, the numerator and the denominator, but I want to reduce first. And I kind of noticed, do you guys notice that this is, I should factor out a negative 1 because I have opposite of x. So if I factor out a negative 1, this is negative 1 times x minus 1, right? Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1, divided by x plus 1 times 1 over x minus 1. And then do you notice what happens here? That this and this are 1, right? If you divide them, x minus 1 divided by x minus 1, and order of operations there, I'd be okay to divide that. So this is, when I divide that, I get 1. I'm going to have negative 1 over x plus 1. And that's the only method I knew how to do when I got a master's degree. And so then my first class that I was assigned to teach, I actually was getting a master's degree at the same time that I was teaching it, and that's when I learned method 2. So I want to show you method 2. Method 2 is called clearing the fractions, and it's pretty slick. So I want to show you that. So it's I would call it clear the fractions. And so we have here x plus 3 over x plus 1 minus 2. So we have what we started with here, or x minus 1. And when you clear the fractions, you multiply by this denominator right there. And you can't just multiply it to the numerator. You have to do it to the numerator and the denominator. So physically, the idea is that I'm going to multiply the top by x plus 1 and the bottom of this fraction by x plus 1. So that's the idea of what I'm going to do. So I'm multiplying this whole thing by 1. And what that's going to do, so look at this. This is, in the numerator, I got a binomial. Do you guys see it? And because I want to drop out that denominator, so I'm going to multiply this by this. And what that looks like is x plus 1 times x plus 3 over x plus 1. And remember, it's a whole number, right? A whole. multiplied by a fraction. So you write this over 1, and so you can really see, oh, the x plus 1 and the x plus 1 divide off and make 1. Well, that's the reason we are multiplying by x plus 1, was for that to happen. And so when we do that, it just leaves us x plus 3. And then when we multiply x plus 1 to the minus 2, we get minus 2 times x plus 1. There was nothing to reduce. And when we multiply this by this, I have choices. I can write it before multiplying it together, or I can FOIL that all together because it's a binomial times a binomial, right? But I'm going to write it as x plus 1 times x minus 2, x minus 1. And the reason I'm not going to FOIL it all the way out is my hope is that it will reduce with the numerator. And so, and the only way that it would reduce it with the numerator is if I factored this. So if I FOIL this together, then I will have to factor it, and then it will be this when I factor it. So I would be kind of chasing my tail if I FOILed it, because I would FOIL, then have to factor, right? And so the reason here I want to multiply this together is that this is a subtraction, and this is not written in factored form, right? Because I have this subtraction. So I have to actually multiply this all together here and subtract it. So minus 2x minus 2 over that bottom. And we're going to have x minus 2x is minus x, and 3 minus 2 is positive 1. Over x plus 1, x minus 1. And then we have that same thing that we had over here, right, with the negative x, and we have these with positive x. So I'm going to factor out of x, and I know that I've kind of run out of room there, so I'm going to draw a little line here. So I'm going to have negative 1 times x minus 1 over x plus 1, x minus 1. And the x minus 1 divided by x minus 1 is 1. So I get negative 1 over x plus 1. Same thing that I had over there. I didn't expect to get something different. And I can see some people are excited and they're saying, could you write this as the negative of 1 over x plus 1? And the answer is yes. They're exactly the same, right? So those are the same. So your choice, if that's whichever one you want to write. If you look in the back of the book, they probably have this in the back of the book, but I would take that just as well. So that's wonderful. Okay, so we did a lovely job on that. And so that was quite, because of course we did it twice, but using two different methods. But that was quite a lot of algebra that we got in there evaluating that difference quotient. Okay, and there's more of them, of course, for you to practice. And so you can go check that out. We're practicing some in class as well. Okay, and so the other thing that they have in 1.1, oh my gosh, I gotten too long. I'm going to do this in the next video.